research data sets are becoming larger, richer, and harder to coordinate. And agentic AI is very exciting and can accelerate biomedical discovery, but only when the research estate is organized, governed, and queryable.
Welcome to the Microsoft Academic Research Exchange. I'm Darcy Ogden. In this video, Shaun Chuah from the University of Glasgow shows us how Microsoft Azure and AI can help scientists spend less time wrangling data and more time moving science forward.
Hi, I'm Dr. Shaun Chuah. I'm a clinical academic gastroenterologist at the University of Glasgow. And today we're excited to share with you Foundry 120, a governed research operating system for translational science that we've built here in Glasgow. Now, this system came about from our work in inflammatory bowel disease, but the problem it solves is actually much wider and applies to how research teams organize their samples, their data, especially with increasingly complex translational studies that we're seeing today. Now, at its core, translational research depends on linking three things. We've got samples, whether these are blood tests, stool tests, saliva tests. We've got clinical data, including phenotypes, disease outcome, treatment, as well as other modalities such as radiology images and endoscopy videos. And finally, we've got experimental outputs such as genomics, proteomics, spatial transcriptomics, all of which are getting more and more complicated. But at its core, each of these in isolation do not mean very much. It is the joining of the three things that is the foundation of translational discovery. A sample becomes useful when we understand the clinical context it comes from, and we can tie that signal into a molecular data set. The problem in practice that we see, though, is that the research estate is fragmented. Freezer and sample logs sit on different systems. Sometimes they're even on paper systems. We've got study databases, EHR exports, manually curated spreadsheets. Oftentimes, protocols and SOPs are on different shared drives, and omics files can come back from sequencing facilities in a variety of formats. In our work, we found that samples were spread across studies, sites, freezer locations. The clinical data that we had, the assay outputs, the spreadsheets, all live in separate systems on different people's workflows. And even a simple feasibility question could take weeks of manual coordination just to find out whether we could run an experiment or not. As of today, Foundry 120 supports 5 clinical studies and over 30,000 samples across Scotland, including Glasgow, Edinburgh, Dundee, and Aberdeen. Foundry 120 is organized into 3 layers. The first layer is organized. This is the real-world research objects that we're trying to track. We've got samples, we've got studies, we've got participants. The next layer is centralized, which is where all our data orchestration layer sits. We put in pseudonymized clinical data and the experimental outputs, imaging data, sequencing files into a single governed structure. And by doing the first 2 steps, we are now able to accelerate our workflows using AI. We've got Helix, an AI agent within the system that allows researchers to get from question to output much faster using natural language queries. Now, importantly, these 3 layers are not sitting by themselves. They are underpinned by a single governance layer, which allows us to control access, provide full audit trails, full file provenance, and this allows us to promote fair data principles in our research workflows. For example, a scientist might have an experiment and they're looking for biopsies from patients with ulcerative colitis who have experienced anti-TNF failure. Now, Helix, our AI agent, is able to perform the lookup as well as the linkage to the clinical data set and return the sample manifest to the scientists. Scientists can then run their experiments, including organoid experiments and spatial transcriptomic experiments. And then they can take those files, register that as a data set, link it back to the participant, and in the future, that allows multimodal integration across modalities such as microbiome data and genomics. And we see this as the foundation that can enable future cross-disease discovery. So let's watch Helix in action. We're going to show you a demo where Helix is going to find data sets, it's going to write and run analysis codes, it's going to encounter an error, and you're going to see it recover from that error. Okay, so let's interrogate our database. What plasma samples do we have for the music study? And can we break them down by the disease group? To accomplish this task, Helix needs to go and join the sample dataset with the pseudonymized clinical data and give us an answer. So this would be an example of a feasibility workflow. So the analysis is happening in a sandbox environment, and Helix can summarize what we have instantly instead of having to do these joins manually. Next, we're going to ask it to do a little bit more interesting work. So we're going to ask it to plot CRP against cfDNA, which is an example of joining a clinical data set to a molecular data set. There's an error here, and Helix is going to recover from that and rerun the code to get you to the output that you want. So that's a quick demonstration of a single workflow within Helix. And what just happened? Helix invokes approved platform tools to access data. It does not browse the database directly, and it's the tools that enforce the permission and controls the data access. So the same data that a researcher can see is the same data that Helix can access, making the governance easy to understand. Second, the analysis that you saw took place entirely within a controlled Azure environment. Helix is able to stage data files into a virtual VM, spin that up, do the analysis, and return the output to the researcher. And the output gets put back into a version-controlled storage system as well. Finally, and critically for researchers, the entire chain is reproducible and auditable. We can see every query, tool call, file input, which version of that file was used, and the generated output. And this gives us the confidence to inspect the entire reasoning chain and ensure that the analysis is accurate. And for us, this is where Azure matters. Azure is not just a platform for hosting. In fact, it is a platform that gives our research IT teams, our data protection teams, and our governance teams a platform that we can understand, assess, and control. So we run our compute off Azure VMs, which allows us to scale the compute to match the workload demands that we're seeing. Storage is handled by Azure Storage, giving us a place to store our spatial transcriptomic data, our digital pathology data, video data, radiology data, and these data sets are very large. And finally, we use Microsoft Foundry to access AI models with explicit controls around permissions, logging, and data residency. And putting the tree together gives us a platform that we think is ready for research applications. And the central point of this talk is that we are observing that research data sets are becoming larger, richer, and harder to coordinate. And we think that AI needs organized research infrastructure in order to unlock the potential of agentic AI here. Agentic AI can accelerate discovery only when the research estate is organized, governed, and queryable. So we started our work in inflammatory bowel disease, but the platform has evolved over time to become disease-agnostic infrastructure. Our rheumatology and oncology colleagues are in the process of adopting this, and our longer-term vision is to enable cross-disease discovery where researchers can ask the fundamental science questions that apply at the deepest levels of biology. For adopting teams, the value proposition is simple. For researchers, we get faster sample feasibility, faster link cohort discovery, reusable data sets, as well as AI-assisted analysis. For institutions, this platform provides a clear governance posture, audit trails, data residency controls, and is a safer AI adoption pathway. To close, if you're experiencing this problem and you'd like to test, adopt, or collaborate on this platform, please do not hesitate to reach out to myself. I would like to thank our University of Glasgow IT services team, our research computing as a service team, our Microsoft partners, our NHS partners, and the translational research teams who have helped shape Foundry 120. My contact details are here, and the landing webpage is available at foundry120.com. Thanks very much.
Thank you, Shaun, and thank you for joining us. Be sure to check out more of our series at the link below.